In the previous video, I talked about big picture what we're going to be doing in this section where we're studying polynomials, and we kind of went over a few different vocabulary words that we'll end up using so we sort of all speak the same language when we learn about these things. But in this video, I want to finally do some of the work. And when I say the work, I mean the steps necessary to come up with the approximate graph of a polynomial for a given equation. Loosely speaking, there's three, I describe them as important characteristics that we want to make sure that our graphs capture. We won't come up with this exact graph of this polynomial, but we'll be able to capture some of its important features. The first important feature that I want to talk about is what's called end behavior. The idea with end behavior is that polynomials, generally speaking, are really complicated. They do all sorts of crazy stuff. They go up and down, they turn around at different spots, they act somewhat erratically in the middle, loosely speaking, of the graph, but eventually they decide to either go up infinitely far or to go down infinitely far. So right now we're not going to focus on all this confusing stuff that happens, loosely speaking, in the middle, but what we're instead going to do is go far enough out to the right of the graph to decide whether the graph goes up forever or down forever. Those are the only two options. And then we'll go far enough out to the left of the graph so it stops kind of oscillating like you see pictured and just determine whether it goes down forever or up forever. That's it. There's really only four options. To the right it can go up and down, to the left it can go up and down. And if you can describe what's going on to the right and what's going on to the left, you've described end behavior, the first of the important characteristics that we want to identify and the only topic of this video. Let me give you a more concrete example. Here's the equation that we started out with, that we don't yet know how to graph. Y equals negative x cubed plus 10x squared minus 16x plus 30. You can always plug this into some online graphing program to figure out what its graph looks like. If I were interested in the end behavior of this graph, I'd be ignoring all of this stuff in here. All I'd be doing is trying to identify when this graph goes far enough out to the left, does it go up or down? What you can see in this case is when we go to the left, the graph goes up. What about to the right? Well, when we go all the way out here to the right, it looks like the graph goes down. That's what these different arrows indicate on the far sides of my graph. The end behavior for this graph is it goes up when you go to the left and it goes down when you go to the right. And if that feels super informal and not like what you'd expect somebody to say in a math class, well, you're right. That's not how we're going to state the end behavior. What we're going to learn are some mathematical sentences that you can write that captures that idea. All I want to say is when I go to the left, it goes up, and when I go to the right, it goes down. The way you write that is you write as x arrow negative infinity. The way this reads is as x tends towards negative infinity. In other words, if you think about your x-axis as this horizontal axis on your graph, and you kind of imagine a negative infinity way out here to the left and a positive infinity way out here to the right, as the x-coordinate heads towards this negative infinity way out to the left, all I'm saying is as my graph goes to the left. What happens? Well, in this specific case, the graph goes up. How can I write that the graph goes up? I'll just say y tends towards positive infinity. Why positive infinity? Well, think about your y-axis right here, and way up at the top of this vertical number line, maybe you can imagine a positive infinity, and down at the bottom, informally speaking, of this vertical number line, you'd imagine a negative infinity. So when I go to the left, x heads towards negative infinity. I go up, y heads towards positive infinity. And when I go to the right, in other words, as x tends towards positive infinity, the graph goes down, y tends towards negative infinity. This looks kind of intimidating with the arrows and the infinity signs and all that, but once you get the hang of it, it's really not that bad. This is just a mathematical way of saying, as the graph goes to the left, it goes up. And as the graph goes to the right, it goes down. And if you can make sense of why these symbols mean exactly that, then you can state the end behavior for any polynomial that we want. To be clear, I haven't shown you how we can look at this equation and tell that it has this end behavior. So far, all that we can do is look at the graph, and from the graph, identify the end behavior and write that mathematically. But by the end of this video, we'll be able to look at this equation and tell why it goes up when it goes to the left and why it goes down when it goes to the right. And once we identify that that's our answer, left, up, right, down, we'll state that answer by writing the mathematical sentences that you see in here in red. So why does this equation have that behavior? Well, really to understand it, what we want to do are look at what are called monomials. Monomials are just a special type of polynomial where we only have one term. So an example of a monomial would be y equals x squared. There's just this one term here. Its degree is 2. Its coefficient is 1. It's a monomial. What does the graph of y equals x squared look like? Well, we've already seen it a few times in this class. It's this standard parabola that you see pictured in front of you. What about y equals x cubed? Well, maybe you're also familiar that that kind of has this S shape. If you weren't familiar with that, I guess you could plot some points, figure out what comes out when you put in, I don't know, -2, -1, 0, 1, and 2, and then sort of connect the dots as best you can. Anyways, I'll take it as a given that y equals x squared is a graph that you understand and y equals x cubed is a graph that you understand. And either from the graph or, I guess now from this equation, maybe we could state the end behavior over here. We're not at all worried about what happens in the middle, loosely speaking here. All we care about is when we go to the left, this graph goes up, and when we go to the right, this graph goes up. So if we wanted to write that end behavior, we'd say as we go to the left, x heads towards negative infinity, we go up, y heads towards positive infinity. And as we go to the right, x heads towards positive infinity, we also go up. So y goes towards positive infinity. That's different than what you see over here, where again, we're not concerned with the middle of the graph, but we recognize when we go far enough out to the right, this graph goes up forever. And when we go far enough out to the left, this graph goes down forever. So we could state its end behavior as when we go to the left, again, x towards negative infinity, we go down, y towards negative infinity. And when we go to the right, x towards positive infinity, we go up, y towards positive infinity. That's x squared and x cubed, but those aren't the only two that we need to understand. We'd also like to understand the end behavior of x to the 4th power and x to the 5th power. But the good news is x to the 4th power looks a lot like x to the 2nd power, and x to the 5th power looks a lot like x to the 3rd power. They have slightly different shapes. This one is kind of a steeper u than the u you see here, and this is sort of a steeper S curve than the one you see here. But as far as end behavior goes, it's identical. We don't care what happens in the middle here. All we care about is the end behavior. This graph goes up when we go to the left, and it goes up when we go to the right. So it's got the exact same end behavior that we see up here. And this graph, we don't care about the middle, but it goes up when we go to the right and down when we go to the left. I said that in kind of a strange order, but hopefully you're okay with me recognizing that this end behavior is applicable to both of these graphs. Really what it comes down to is what's called the parity of the degree. All the parity refers to is whether something's even or odd. So x squared, this 2 is an even number. X to the 4th, this 4 is an even number. So that's why these guys have the same end behavior. The 3 in x to the 3rd and the 5 in x to the 5th are both odd numbers. So that's why, informally speaking, they have this end behavior. We can kind of generalize these findings by talking about how there's really only 4 different end behaviors for monomials. All we care about is whether the degree of the monomial is even or odd. So whether n in this formula is even or n in this formula is odd. And whether the coefficient, the number out in front of the x, is a positive number, so if a is positive, or a negative number, so if a is negative. That leaves us with 4 different options: n even a positive, n odd a positive, n even a negative, and n odd a negative. And if you can come up with those 4 different end behaviors, you can completely describe end behavior for any monomial, which turns out is all we need to describe the end behavior for any polynomial. So let's take these one at a time. What if we have an even exponent and a positive coefficient? Well, we've already seen 2 cases of that, right? This case and this case. In both cases, our coefficient is a positive 1, and our exponent is even, 2 and 4 in the 2 that's pictured. So the end behavior is exactly what we wrote here. Loosely speaking, the graph is going to kind of look like this. And when we go to the left, the graph is going to go up. And when we go to the right, the graph is going to go up. The other case that we've seen already is when n is odd and a is positive. Because again, in this case and in this case, we have this implied 1 in front of the x term. So the coefficient is a positive 1. We have odd degree and a positive coefficient. We have this second case. Loosely speaking, it looks like this, but we're not concerned with what's going on in the middle. We're only concerned with the fact that when we go to the left, the graph goes down. When we go to the right, the graph goes up. Again, not to beat this to death, but the way that you would write that is goes to the left means x approaches negative infinity. Goes down means y approaches negative infinity. Goes to the right means x approaches positive infinity. Goes up means y approaches positive infinity. And maybe you're like, yeah, okay, that works out fine as long as my coefficient is positive. But what if this were a negative number here? Well, think about what that would do in terms of transformations, right? We'd be multiplying all the y coordinates by a negative number. Any height that used to be positive would now be negative, and any height that used to be negative would now be positive. A negative coefficient would have the effect of flipping these graphs vertically. So if I were in the case where n is even but a was negative, it would look a lot like what's pictured here, except it would be flipped upside down. So loosely speaking, my graph is going to look like this. I'm not too concerned with the shape of the graph. All I want to do is describe the end behavior, and the way we do that is we talk about when it goes to the left, the graph goes down, and when it goes to the right, well, the graph also goes down. The fourth and final case to consider is when n is odd and a is negative, so it looks a lot like what we see here, except it's been flipped vertically. So the picture you might want to keep in your mind is something that kind of sort of looks like this. Don't worry too much about the shape, just keep track of the fact that when we go to the left, the graph goes up, and when we go to the right, the graph goes down. 4 different types of end behavior, which cover every single scenario that we could possibly have for any monomial. And you're like, yeah, that's great, but we don't want to describe the end behavior of a monomial. We want to describe the end behavior of a polynomial. Well, good news, it's not any harder. Remember this original graph that we looked at that we know the end behavior of? It comes from the equation y equals negative x cubed plus 10x squared minus 16x plus 30. If you look at each of these different terms, some of the terms are even, some of the terms are odd, some have negative coefficients, some have positive coefficients. It might seem really complicated to explain the end behavior, but it turns out it's not at all. How do we figure it out? Well, in short, the largest degree term always wins. What am I talking about? When we're talking about end behavior, we don't care about what goes on in the middle of the graph, meaning we don't care what happens when the value of x is relatively close to 0. All we care about is when the value of x gets really, really large, positive, meaning we're way out to the right, or really, really large, negative, meaning we're way out to the left. So think about each of these different terms when the value of x is some really large number. Maybe think like 1,000 or something. Negative 16 times 1,000 is a really large number. It's negative 16,000. And 10 times 1,000 squared is much larger because 1,000 squared is 1,000,000 and 10 times 1,000,000 is 10 million. But all of those pale in comparison to 1,000 cubed. 1,000 cubed is a billion, which is so much bigger than 1,000 squared, even after we multiply it by the 10, that this term is going to completely overpower these other terms. When your value of x is really small, like, I don't know, 1, this term has the biggest effect on the value of the thing because 30 is bigger than negative 16 or 10 or negative 1. But we're not concerned with that. When the x's are small, different terms kind of take control of the height of the polynomial, loosely speaking. But for our purposes, all we care about is the end behavior. And the end behavior always corresponds with really, really large x values. And when we have really, really large x values, whether they're negative or positive, the leading term always wins. It always dominates. What does that mean? It means that if somebody asks you for the end behavior of this polynomial, you can completely ignore all of these terms. All you have to do is look for the term with the largest degree. Whatever that term's end behavior is, will determine the end behavior of the entire polynomial. And since that term is really just a monomial, and we learned above how to categorize the end behavior of any type of monomial, we're done. You take a look at this polynomial, you just look at negative x cubed, you recognize that a is negative and that n is odd, so really we're in this case. So this graph is going to go down when we go to the right, and it's going to go up when we go to the left, which is exactly what we see pictured. Even if we didn't have this graph, we would know that eventually it's going to go up to the left. So we could say as x tends towards negative infinity, y goes towards positive infinity, just by looking at this first term. Similarly, even if it wasn't pictured, we'd know that when it goes to the right, it goes down. So as x tends towards positive infinity, y tends towards negative infinity. Because we know the behavior of negative x cubed, because we have this generalized behavior for monomials. That's it. To see if that made sense, let me show you one more example, and if you can follow this, you're good on everything from this section. Consider the graph of negative 2x to the fourth plus 20x cubed minus 160x minus 10. We're not going to try to graph this thing, at least not yet. All I want to do is describe the end behavior. So we're not going to concern ourselves at all with what happens in the middle of the graph, But we are going to wonder, does this graph go up when we go to the right or down when we go to the right? Does this graph go up when we go to the left or down when we go to the left? And we can figure all of that out just by looking at the equation. Specifically, the first term of the equation, the term with the largest degree. I don't care about this 20x cubed or this negative 160x or this negative 10. All I care about is negative 2x to the fourth. Because the exponent is even, I know it's going to go in the same direction when it goes left and right. And because this leading coefficient is negative, I know that it's going to go down when it goes to the left, and therefore also when it goes to the right. Here's a picture of the end behavior of this graph. If you wanted to state it, what you would say is as x heads towards negative infinity, in other words, when we go to the left, y goes to negative infinity. In other words, the graph goes down. And as x heads towards positive infinity, when we go to the right, the graph also goes down, y tends towards negative infinity. That's what I have drawn with these arrows right here. You want to see the actual graph of negative 2x to the fourth plus 20x cubed minus 160x minus 10? Here it is. Not exactly what you see pictured in purple here, but it does capture the end behavior, right? I don't know what's going on in the middle of the graph, all sorts of confusion that I'll learn in future videos, but when it goes to the left, it goes down. When it goes to the right, it goes down. That's the end behavior that I captured right here. The good news is end behavior questions can't get any more complicated than what I just showed you. The bad news is that there's more characteristics of these graphs that we want to capture, not just end behavior. But I'm going to save those characteristics for the next video.